Hello and welcome back. In this video we are going to talk about some applications of differential equations. We are going to introduce the idea of the plane method, and at the same time we are going to talk about the chain rule. This idea of the plane method is directly related to the chain rule that you may recall from Calculus 1. So the follow-up question is, what is the relation? What relation is hold between these two ideas? How can we apply this to differential equations? And we are going to wrap up with several application problems. So let's get started. So let's talk about the chain rule. So as you can see, when we are taking the derivative of an outer function, we got to multiply it by the derivative of the inner function. So when it comes to the chain rule, there are two main parts. We always have an outer function and we have an inner function. We start off by taking the derivative of the outer function, and we continue on by taking the derivative of the inner function. So maybe this sort of kind of complicated notation can be a little confusing to you, but for example, I can add a really short example. So let's say that we want to take the derivative with respect to x of cos of 3x, right? So this is going to be equal to negative sine 3x. Okay, so this is going to be the outer function, the trigonometric part, but now we are not done yet because we got to take the derivative of the inner one, which is 3x. Thereby we have 3, and based using the chain rule, we have negative 3 sine of 3x. So that's how the chain rule works, and hopefully you are not too rusty with like concepts that we covered back in Calculus 1. But the important part here, like the brand new idea, or at least what we want to focus on here, is the plane method. So let me introduce you this idea. So I am going to highlight this in green. So right here we have dv over dt. So this is going to be the derivative of b in terms of t, right? The derivative of b with respect to t. So, and then I am going to do it in yellow. Right here, we have the derivative of b with respect to x, and then multiplied by the derivative of x with respect to t. I am going to do it in blue. So, right here, the dv over dt is going to be like our final answer. The final result of the what would be the chain rule. So b is going to be the outer function, and x is going to be the inner function. So let's write that down. So we have this is going to be the outer function, and in blue we have the inner function. So that's all there is. So it's not as complicated as it may look. So you can also set the dx over dt. You can naturally set it equal to b, because we know that the derivative, the first derivative of x is going to be equal to the velocity. So we can essentially substitute that right there. But I will explain that to you later on with the examples. So let's start off by working on a really simple and straightforward algebra involved problem. So our first problem reads, suppose that the second derivative of x with respect to t is equal to 18x cubed. Our initial conditions are x of 0 is going to be equal to 1, x prime of 0 is going to be equal to 3, and we are asked to find a formula for b in terms of x, then find a formula of x in terms of t. So this is essentially the direct application of what we understand under the name of the plane method. So let's see how this goes. So first of all, let's write that down right here. So we have the second derivative of x with respect to t. We have 18x cubed. So first of all, we know that the second derivative, what is that? Well, we know that the second derivative, we got to take into consideration the fact that x is a position function. Thereby, if we are taking the second derivative of the position function, as you may probably recall from calculus 2, you got it. It's the acceleration. So this is the acceleration. So thereby, if we take the first derivative of the velocity function, that is also going to be equal to the acceleration. So let's write that down. So we have this like this, right? So all this is equivalent, okay? So now let's write in red what we get for the plane method. So let's write this again one more time so that we do not forget. So we have dv over dt, and we have dv over dx once again. Now the inner function is going to be the dx over dt. And then in the second step, let's simply replace our dx over dt by simply b. So this is the relation that we have, right? And we are asked to find a formula for b in terms of x. So we are one step closer. So let's go ahead and substitute everything. So as we defined our dv over dx times b, that is going to be the second derivative, right? And then that is going to be equal to 18x cubed. So at this point, we just got to solve this really simple sort of differential equation. And as you can see, it's really easy to separate these parts. So this is a separable. We will see this concept later on in future problems, and we will talk about this a little bit more when we start thinking about the different techniques that we can use to solve various differential equations. But for now, let's work with separable differential equations. So I have it right here. Now what we got to do is we simply, this is like elementary mathematics. We just got to essentially, let's say, put the v's on one side and put the x's on the other side. So we have it right here. We have v dv. We have is equal to 18x cubed dx. Now, as we saw before, we just got to take the integral of this so that we get v squared over 2. We can add a constant either here or on the other side. So now this we are going to integrate with respect to x. So we have this. Half is going to be 9 2, so we have 2 halves. Multiply thing by 2, so that we have b squared is going to be equal to 9x to the 4th. And yeah, but we got to include a constant. It doesn't matter where, but we got to include it sooner or later. So that's wonderful, because we have what we were looking for. And we could simplify a little bit more and take the square root of both sides, right? We can take the square root of this, so that we have b is going to be equal to square root of 9x to the 4th plus c. And this is the equation, essentially, that we were asked to find. So at this point, since we are given the initial conditions, we can find the constant as we would for any integral, essentially, as you may recall from previous classes, right? So we have x of 0, so the position function, at times 0 is equal to 1, and then the x prime of 0 is equal to 3, meaning the velocity. So let's go ahead and substitute. So we can do so right here. So we have one more time. So velocity 3, position 1. So we can write that down. So we have 3 is equal to, and we have a square root of 9 times 1 plus c. At this point we can raise everything to the second power, right, squared. So we have 9 is equal to 9 plus c. So c is going to be equal to 0. So we don't need to worry about the constant in this case, which means that we can simply write it like a square root of 9x to the 4th. So we can simplify this a little bit more. So we have velocity is going to be equal to 3x squared. This is a great advantage because the second part of the question is asking for a formula of x in terms of t. So now we are going to take the b is equal to 3x squared, and we are going to write b as the derivative, as the first derivative of the position function. And then we write down it's equal to, oh my bad, it's going to be equal to 3x squared. So one more time, this is going to be separable, another separable differential equation. So we got to integrate these two sides. So this is really easy because we can rewrite this. We have the integral of this, of the x to the negative 2. And we can have the x, of course. So we have the integral of dt, which is really straightforward. So we have 1 over 3. Right here we have negative, and then here we have t. Do not forget about the constant. And then we can continue on right here. So we have negative 1 over 3 times 1 over x. And then here we have t plus c. If we please, we can elevate everything to the negative 1 so that we are more comfortable, you know, having the negative 3x right here. And then here we have essentially 1 over t plus c. We don't care at all about the constant, because it doesn't matter if it's 1 over c or c squared. It's a constant anyways. So let's isolate and find for x. So we have negative x is equal to, and then let's divide everything by 3. So we have times 3. once again, the constant is just the constant, so we don't care about it that much. So we have x is equal to 1 over 3t plus negative 1 over 3t plus the constant. So this is going to be our final answer. This is going to be the function of x in terms of t, the position function. So that was a really straightforward problem. Now let's jump straight into a more complicated problem or a more involved problem, but under the same principle. So problem number 2 reads, suppose that a rocket of mass equal to 1,000 kilograms is launched straight up from the surface of the planet Trantor with initial velocity 10 kilometers per second. The radius of Trantor is 3,000 kilometers. When the rocket is r meters from the center of the Earth, it experiences a force due to gravity of magnitude gm times m lowercase, which is essentially the mass of the rocket, right? So divided by r squared, where we are given that gm is equal to 6 times 10 to the 14th meters cubed over second squared. So the first part is asking us to formulate the initial value problem for the rocket's position. Bullet point B, we have find the velocity of the rocket as a function of position, and the very last one is asking us for the how far away from the Earth is the rocket when it stops moving and starts to fall back. Okay, so for these problems, the setup is the most important part, because if you were able to understand the previous problem, then you will easily solve this one as well. So let's start off. So we have that we are given that the mass is going to be equal to 1,000 kilograms, okay? And then we know that the radius of Trantor is equal to 3,000 kilometers. Let's write it as 3,000 times 10 to the third meters, because we should stick to SI units. Remember that. So when the rocket is r meters, now it's telling us from the center of the Earth, it experiences a force due to gravity. So our force right here is going to be equal to gm times the mass, right? The mass, and then this is going to be over r squared, okay? And we can go here and write down the following. So we have 6 times 10 to the 14th meters cubed over second squared. We are given that as well. So I think that I wrote way too big, but I think that we have enough room to answer the first part at least. So the very first part consists of our mass times acceleration. Our force is equal to mass times acceleration. So we get to write that down. So we have m. We multiply that by the second derivative of the position function. So we can write that down. Is equal to, now we got to account for this force due to gravity of this given magnitude. So let's write that down. So we have gm uppercase, we have the m, that is the mass, right, over r squared. So right here, as we can see, we can cancel out our mass. It's real important to take it into consideration, but at this point we can just simply cancel these things out. So we can go ahead and substitute what we were given for negative, well, for GM. So we have negative 6 times 10 to the 14th over r squared. So right here, something that I wanted to point out is that while x is the position function, we are talking about radius, right? Radius is our position function essentially. So please do not do this like automatically, like without thinking, because you may kind of get scared at this point if you wrote x instead of r. So we got to be really consistent in mathematics. It's really important to be consistent. So let's change this to r instead. So there we go. As we can see, once again, we have something that will be separable, but don't move that fast. First of all, let's work with the plane method. But before jumping into the plane method, since we are asked to formulate the initial value problem for the rocket's position, every single time that we are asked to formulate an initial value problem, there is the differential equation, but we also need to take into consideration the initial conditions. So let's see. So we know that the initial velocity is going to be 10 kilometers per second. Okay, so we know that x prime of 0 is going to be 10, and then let's write it as 10 times 10 to the third meters per second. Once again, we got to work in meters, not in kilometers. And then the initial position is going to be the radius, right? Which is equal to 3,000 kilometers. Once again, 3,000 times 10 to the third meters. So once again, hopefully you at this point you know that you got to be consistent, and you cannot use x every single time to represent the position function. So once again, I am going to erase the x because it's not appropriate in this case. So instead we're going to write it as r, so r of 0, r prime of 0. So we've just answered part A. Now for part B, we need to use the plane method to find the velocity of the rocket as a function of position. So right here we have our plane method. So let's go ahead and substitute everything so we can go back. So let's write it down as dv over dr times dr over dt. Once again, that is equal to velocity minus, and whatever we were given for gm, negative 6 times 10 to the 14th, 6 times 10 to the 14th over, and then we have r squared. Once again, it's separable. I am going to go real fast on this part. So 6 times 10 to the 14th, our dr is going to come over here, r squared. Let's go ahead and integrate both sides. So we have b squared over 2, and then here we have negative 6 times 10 to the 14th. Here we are going to have negative 1. This is going to change to positive. So I am just simply taking the integral, so we get plus c. As I was saying before, you can add the constant either on one side or the other one, or even in both sides. You don't have to worry so much about the constant. It's like it works totally different to any sort of variables here. So as you can see, we have this. At this point, we can go ahead and because this is going to be the velocity of the rocket as a function of position. Obviously, as I was saying before, you can take the square root of both sides. You can multiply everything by 2, but this is essentially the relation that we have. But now we got to substitute the initial conditions. So let's go ahead and do so. So after substituting the initial conditions, this is what we get. We can pull off our calculators and find for C. So I got C is equal to negative 1.5 times 10 to the 8th. Remember to use scientific notation, it's really important. Now let's come up with our final answer, which is going to be b squared is equal to 6 times 10 to the 14th, r negative 1 to the negative 1, negative 1.5 times 10 to the 8th. Now for the very last part, we are asked to find how far away from the Earth the rocket is when it stops moving and starts to fall back. So for that one, we know that it's going to stop moving when the velocity is equal to 0. So we just need to substitute and find for r when the velocity is equal to 0. So the left-hand side part is equal to 0. We have 6 times 10 to the 14th times r to the negative 1. We have negative 1.5 times 10 to the times 10 to the 8th. Now we can simply do some algebra right here. So we have 1.5 times 10 to the 8th is going to be equal to 6 times 10 to the 14th. And then we have r to the negative 1. We can isolate r. So we are going to get r is going to be equal to 6 times 10 to the 14th over 1.5 times 10 to the 8th. And that's essentially what we get, and that is going to be the answer for C. So I think that's all I have for this lesson on phase plane method. I really hope that it was helpful for you in some way, and I will see you soon.